we will talk about set point regulation. So we have, I will go very quickly on this slide because it's a usual set point regulation. And so this is a Watt regulator, and I will go quick because we don't have time due to this problem. Anyway, so to understand regulation and to understand integral action, I suggest to start with a very simple example, .x equal u plus d. It's just for people who are not familiar with integral action. Probably not many people in this audience. And we have an output that we want to track, which is the state, x, which belongs to R. And the control also belongs to R. The D is a disturbance, which is a constant in this framework. And given a reference YR in R, what we want to do, our goal is to design a feedback, U, or control, such that this output Y follow a reference YR. Actually, if we use a simple proportional controller, then we will get an equilibrium that will be stabilized, but we will miss our goal, which was regulation. Indeed, you can see that Y won't go to YR due to the disturbance. However, if we add an integral action, so this integral action, it has a state, Z, and Z dot integrates the mismatch between your output and the reference, then you create a new equilibria. And since you are converging to an equilibria, at this equilibria, Z dot has to be equal to 0. And if Z dot is equal to 0, then Y is equal to YR. And we understand why integral action and stabilization of a cascade of your system plus integral action solve your problem. And this very simple example, just to refresh your memory, now we will try to apply it to some infinite dimensional system. And this will be my talk. So we will first see some general approach for abstract Cauchy problem. Then we will apply it to hyperbolic PDE, and we will see how we can handle it when we have a saturation in the control. So first, for an abstract Cauchy problem. So this Cauchy problem is given like that. We have .x is equal to an operator, AX, plus BU, B is a control operator, and again, we have our disturbance. The output Y is given as a linear map, C of X. So D, this perturbation is unknown, and our operator is linear. So it has a domain, D of A, and it is in a Hilbert space, X. U is a control. We will take in this presentation U in Rm. Most of the results can be extended to more general class of input, but not the last part of the presentation. I mean, from my knowledge. So B is a linear operator, which will be most of the case, in most cases, bounded, but bounded in theory, but on some application, we will see that we can use it, all those theory, with boundary control. C is also a linear operator. Okay, so what we want to do is again to design an integral control law. So we introduce this integral action. So Z dot Y of t minus Y ref. And the control will be at the beginning just a function of Z. And what our aim is to find the parameter, small parameter ki, that will be a coefficient, and a direction for the control. So this direction will be a matrix, such that for any reference, we get regulation. So of course, since we have introduced a new control, a new state control. So Z, our state space has been extended, and now we will note XE as an extended state space, which will be also a Hilbert space. So if we look at the closed loop system, it takes this form. So we have in blue the, I could say, perturbation. Of course, the second one is not a perturbation because it is a reference, but in the regulation framework, this can be seen as a perturbation. And we have D, the perturbation that acts on the dynamic. the new operator has been extended like that. So you see that there is this C that's popping up due to the integral action, and we have the control. So now the question, can we find Ki and the parameter Ki such that the AE, so this operator, is a generator of a semigroup, and also such that this semigroup is exponentially stable. And also, in the second time, we will ask ourselves if the regulation is obtained. So if indeed the output y of t converge to the reference. So in the second part of my presentation, I will address the regulation, not the regulation maybe, as you will see, but at least the stabilization when AE is not exponentially stable. Okay, so as a primary assumption we will make, we will assume that the open loop operator A, as a starting point, we will assume it is already exponentially stable. So we will assume that there exists C and lambda such that this equation hold. Actually, if we go back to our system, we see that this, due to the structure of this system, we can show that the stability of the open loop system is actually a necessary condition for our problem to be solved. And so this assumption is very strong, but it can be obtained via a preliminary feedback, for example, a proportional one. And as I said, in the second part of my presentation, I will assume weaker assumption than exponential, but still we will assume stability. Okay, so this topic has been studied by many researchers over the years. So I think that for infinite dimensional system, we can trace back this problematic to the work of Pohjolainen in Finland, where he has shown that the regulation is obtained for if A generates an holomorphic C0 exponentially stable semigroup. Later on, Chenzong Xu, a colleague from the LAGEPP in Lyon, and with one of his students, Gerby, in 1995, they obtained also a result for general exponentially stable semigroup. And more recently, so this has been tackled in a way more general context, for example, by Lassi Pononen. And also, if we stick to some specific PDE with boundary controls, this has been addressed by Jean-Michel Coron, Georges Bastin, Christophe Prieur, Hugo Lachemy, Amaury Hayat, Luca Brivadis, Nicolas Vosprangeux. So in the context of some specific PDEs, and also for Port-Hamiltonian system, again by Lassi Pononen, and also with Jan Legorek in a recent paper with the Lyapunov approach. This Lyapunov approach is exactly what I will introduce later. It's not exactly the same than the one that has been followed by Jan and Lassi, as you will see. And I want to say that the integral control also for nonlinear system in infinite dimension is still an active domain of research. For example, recently with Mattia. Mattia was one of our PhD with Daniela Stolfi and on this topic. Okay, so let's go back to the Xu-Gerby result in 1995 to understand what we want to do. So they claim that if A generates a C0 semigroup which is exponentially stable, moreover, if B is bounded, C is A admissible, so which means that we have that C can be upper bounded by the graph norm associated to A. And also that we have this integral which is bounded, which gives you admissibility. So this gives you well-posedness of your system with the integral action. And also if the rank condition holds, so for people who are doing regulation, they are well aware of this type of property. So CA minus 1B needs to be full rank due to the fact that remember that B and I mean the output and the input are in Rm. Then, based on those three assumptions, Xu and Gerby have shown that there exists a parameter Ki star, such that if you pick the direction of your control to be exactly Ca minus 1b minus 1, the output regulation is obtained. And so the remark we can make is that this result needs to be bounded. And actually, the extension to boundary control is quite difficult if we follow this approach. And the proof follow a spectral approach. And extension to nonlinear system may be difficult. Also, the parameter ki star may be difficult to estimate. You need to compute the resultant. So the question now that we will address is, can we follow a Lyapunov approach? Actually, and this will be the first part of my presentation, what we can say is that if A, you remember, we assumed that A was generating a C0 semi-group which was exponentially stable. So we know that there exists a P, a bounded linear self-adjoint positive operator, such that this Lyapunov equation is satisfied. So the question now, if I give you this P, are you able to construct a candidate Lyapunov function for the complete system? And this is what we will do in this theorem that we obtained in 2020 with Alexandre Teranjan, Chenzong Xu, and Valérie Dos Santos. So we put ourselves in the context of Xu-Gerby 95. So we assume those blue assumptions. Then we can show, and we assume, moreover, that we have this P, the Lyapunov operator associated to A. Then we can show that there exists a bounded linear operator M, which goes from X to Rm, and a matrix Ki and a positive real number P, Ki star, and nu E, such that we get a Lyapunov function for the closed loop system. This Lyapunov function, as you can see, so it takes the first part of the Lyapunov function associated to the operator A, plus something, and this something is related to the M that we know it exists. And I will give you its exact expression in a minute. So we have a Lyapunov function for the overall system, and we can compute. This is important to know that we can compute it, and that leads that give us stabilization. So let's have a look at the proof and to see how it works. So the time derivative of this Lyapunov function, so we have this v dot. This v dot gives you the negative part in x, because remember that v was the Lyapunov function associated to A, plus the time derivative of this part, the part with m. So we have z minus mx times z dot minus mx dot. And if we replace z dot and mx dot by what they are, we obtain this first equation that is that depends on x, plus coupling term. So the idea of our approach is to select m such that this part disappears. So actually, it's very easy. You just need to solve this equation. And this equation is solved if you pick m equals ca minus 1. Remember that A is exponentially stable, which means that 0 belongs to the resolvent set, which means that this m actually is well defined. Actually, since C is A bounded, this m, you can show that it is bounded. So we have not finished, because W dot, now we have something negative here, and now lots of coupling term. We have even a quadratic term in Z and coupling term. This quadratic term in Z, we can make it negative if we pick capital Ki to be equal to Ca minus 1b. This is the direction obtained by Xu-Gerby. Moreover, the two remaining blue terms, you can see that they are multiplied by Ki. And moreover, the negative part in X does not depend on Ki. So actually, you can show that taking Ki sufficiently small, this W dot is negative. So this is a way to obtain a Lyapunov function for the system with an integral action. Just a comment, this construction, we have not invented it, we have applied it to the PDE, but in fact, it comes from techniques that have been applied for way more difficult system in nonlinear settings for finite dimensional system, and it's named forwarding. So it has been developed by Miroslav, by Laurent Prali, and Mazank. Okay, so the interest of this Lyapunov function is that we can optimize this Ki. We can explicitly give one value. Actually, this Ki with this approach can be given the optimal one, so the largest Ki that we can use is given here. Moreover, actually, if we follow the proof that I just gave you before, B-bounded, why do we need B-bounded? It's for the well-posedness of the closed-loop system, but also, if we look at the Lyapunov approach, in fact, what we really need is just an ISS-Lyapunov function. As I promised, I will talk about ISS-Lyapunov function. This is where I will talk about Lyapunov function. If I replace the previous theorem, if I forget about the well-posedness, and I just say I have an ISS-Lyapunov quadratic ISS-Lyapunov function in the sense that this property is satisfied, then the W function that I considered before is again a Lyapunov function. So, of course, one interesting question to know is, okay, given a system, is it easy to find an ISS-Lyapunov function? And to answer this question, the best solution is to look at the result obtained by Andrei Miroshenko and Fabian Wirtz, and you will know if it is possible. So let's see if this procedure can be applied to a well-known system, for example, to hyperbolic PDEs. So this is the third part of my talk, and we consider general hyperbolic PDE, first-order hyperbolic PDEs, that are given like that. So we have so phi is m functions. Time derivative of phi is equal to a matrix which depends on S time spatial differentiation of phi and a linear term. S belongs to 0, 1, and T 0 plus infinity. So it's a usual hyperbolic PDE. We have an input. The input shows up at the boundary. And so this is this U. So we can rewrite in the framework of Jean-Michel Coron the action of this input. It depends on a matrix K, which gives you how things are related on each side of the spatial domain. And we have an output that we want to regulate, which depends on a boundary condition of our function phi. And we have a perturbation, dy, db. The parameter of our hyperbolic PDE. So, of course, our system is hyperbolic, which means that we have conditions on this matrix lambda 0. So the eigenvalues are real, etc. And also, we need those S function to be C1. And all the other matrices are constant. And we want to know if we can apply the exact same procedure as before to this kind of system. So we want to introduce an integral action. So what we want to do is find the capital Ki, the direction, the small ki, how high the power of this control, such that there exists a unique solution. There exists an equilibrium which is exponentially stable for any perturbation, and such that the regulation is obtained. So, our we will work on this Hilbert space, the usual Hilbert space for this type of system, so L2 space. We add the part which correspond to the integral action, and we add also this new norm, in which we add the norm associated to the finite dimensional part. We also introduce a smoother space, H1. And the results that have been obtained by Bastin and Coron in the book, you can find it in the book published in 2016, is related to well-posedness. Okay, so we have solutions for the closed loop with, even though the control is not bounded, in this specific case, we can show well-posedness of the overall system with the integral action. And so remember, we need to start from a Lyapunov function for the open loop system. And to obtain this Lyapunov function, again, in the same book by Bastin and Coron, several sufficient conditions are given, which allows to obtain a Lyapunov function. And you remember, we need an ISS Lyapunov function. So what you can do is just look at what they showed in their book, and just make sure that the Lyapunov function you obtain is ISS. And this is indeed the case. So we will assume the existence of this Lyapunov function, and you can show that depending on those, so you remember lambda 0 and lambda 1 were parameters of my PDE. So the lambda 0 was the one related to the infinite dimensional part, and lambda 1 is the one related to the linear part. So you can obtain some sufficient condition for this existence of an ISS Lyapunov function for the open loop system. And actually, so in the book by Coron, this S is just assumed to be negative, semi-negative definite. In our case, since we want an ISS Lyapunov function, we need strict inequality. So if you pick your PDE, if you can solve this Lyapunov type equation, then you get your Lyapunov function for the open loop system. And now we will try to apply our procedure. And you remember our procedure was depending on several conditions. What I call the rank condition, which was C A minus 1B needs to be full rank. This translates in the context of those PDEs to two matrices, T1 and T2, that needs to be full rank, those two matrices. So I won't go in deep detail on this slide. It's just that this is what you have in the abstract context, particularized to this specific PDE to show that CA-1B is full rank. Of course, B is boundary, C is boundary, so it's not that easy, but you can obtain a kind of similar assumption. And so T1 and T2 need to be full rank. And you get the result that if T1 and T2 are full rank, then you get the regulation. And actually, this result was new in the sense that it was not possible to prove it without the Lyapunov approach. So we get the regulation. We get well-posedness, and if we take the initial condition in a smoother state space, then you get the convergence of your output to the reference. Okay, so in this context of hyperbolic PDEs, B bounded has just been replaced by L2 ISS Lyapunov functional. This is the message. And the full rank, CA-1B full rank, has been replaced by T1 and T2, two matrices that you can compute based on the data of your model. Those two matrices full rank. So this approach can be applied to some specific PDE. And for example, as an illustration, we can consider the de Saint-Venant equation as the one that has been studied by Coron and Bastin. So this is the linear one, the linear Saint-Venant equation. So these are the two PDEs. We have the boundary condition, the measure output to be regulated in this specific case. And what is interesting to see is that in 2008, so Valérie dos Santos and also Jean-Michel and Bastin, they have tried to introduce an integral action on this system, and they ended up with some specific constraints on the parameter of the system. So with this Lyapunov function, which is based on the M parameter, as the M function that we have computed, then it is possible to show that we can still obtain regulation for a way larger class of parameter. So this shows the interest of this Lyapunov approach on this specific example, the Saint-Venant equation. Actually, as I mentioned at the beginning, the use of Lyapunov function is very interesting if you want to handle nonlinear system, And this is what we have done in 2017, for example, in the case of a nonlinear transport equation. So for this system, it was possible to show that you can still achieve regulation for small perturbation and by adding an integral action and following a Lyapunov approach. I won't go into deep detail on the result we obtained with TRIN in 2017. Actually, this approach, so this was applied just for this system, but this approach, the exact same approach, has been followed by Nicolas Van Sprange and Luca Brivadis in a recent paper that has been published in, I think, in SIAM, maybe, in 2022. If you are interested, you should have a look at this very nice paper in which they consider quasi-linear system for general class of quasi-linear system. So now that we have understood how to construct the Lyapunov function to deal with integral action, I want to talk now about saturation. So we will, our system now is the same system as before. We have an output, we have a linear part, but now the control acts through a saturation operator. U now will be taken in R, not Rm to simplify. And the output Y is in R. And the saturation is simply defined as the usual saturation with a level at 1. So the control for PDE system subject to input saturation has been studied by many researchers, and I think that we need to mention Slemrod, who I think was one of the first who obtained some results related to input saturation. And this is a very nice paper, the one in 89. Of course, Logman, Ryan, and Tonley in 98. Lazieka, Sedman in 2003, and some recent researcher, so I would say Christophe Prieur school, with the Swan, Sophie Tarboyesh, João da Silva, and recently some of the name. So this is an important topic. And if you want to add the integral action, this makes things quite difficult, as you will see. So now we add the integral action and we have the saturation. So we have the two effects. So if we can summarize our system in this form, so we have a linear part. The linear part is the one that we had before. I put 0 here now because I don't put the action of the control, since this one is saturated, so it does not belong to the linear part. And we have a nonlinear function. So this nonlinear function is the saturation. So the saturation is a good nonlinear function because it is Lipschitz and it is monotonic. Actually, we will use both properties in the following. So the question is, can we still obtain global exponential stability for this nonlinear system? And also the second question is, and what about asymptotic stability? And if we do just asymptotic stability, what can we say about the regulation? This will be the two small topic I will talk now. So obtaining global exponential stability. Our system takes this form, so we have a linear part plus a nonlinear part, and this nonlinear part is saturated. So we end up with this complete system is a nonlinear semigroup. And we have this necessary condition that we have obtained in 22, which is if the origin of the system is globally exponentially stable, which was our goal, then necessarily this F needs to generate a C0 semigroup which is exponentially stable. So due to the fact that we have here a saturation, if we want global exponential stability for this nonlinear semigroup, then F needs to generate a C0 semigroup which is exponentially stable. And we can have a sketch of the proof, which is quite simple. So my solution to this nonlinear PDE can be written like that. So we have this nonlinear semigroup, which will be equal to the linear semigroup plus the integral term, in which we have, again, the linear semigroup and the nonlinearity, which shows up here. And if we look at what we have, so we replace this by the norm that we have, this estimate. And so this guy goes on the left, this guy goes on the right, and we replace it by the norm. And we see that we have an homogeneous in the state XE bound, homogeneous in the state XE bound, and here something which is bounded. So if you pick XE very large, then this thing goes away, because this part will dominate. And you end up with this inequality, which exactly means that the linear part needs to be exponentially stable. And this is a problem, because if we go back to our F here, we see that we have a 0 here. So this means that if we just try to apply what we did before, then we have no chance. We have no chance to obtain global exponential stability. So what we need to do is to modify our approach, and we will see later on that we will do anti-Dept technique. So now a sufficient condition. If we have an operator, nonlinear operator, that is written as a convex combination of two linear operators, so assumes we have this property, then if there exists a P, a bounded, which coercive is important here, linear self-adjoint positive operator satisfying two Lyapunov inequality for each of the linear system, then we can say that the origin, I don't talk about well-posedness, but the origin of the nonlinear semigroup, if it exists, is globally exponentially stable. So in this theorem is quite trivial to show. It just uses the convex combination, and it uses the coercivity of the Lyapunov functional P. And actually, it's an open question to know if the same result could be obtained without assuming coercivity. So this is an interesting sufficient condition for stability. And let's try to see if we could modify our integral action to apply this result. Actually, the idea is to add this blue part to the integral action. So the integral action was the black part, the one we used before, and now we add the blue part. The blue part allows us to modify it and to increase its convergence speed. For Z large, this guy converges to 0. This is what we call an anti-Dept technique that has been introduced for finite-dimensional system. The other thing which is interesting is that if Z is small, then the saturation is not active, and this blue part goes away. So basically, we have added a term which disappears when Z is small, and which is stabilizing when Z is large. So this means that we recover our integral action for small z, and we have the stability, the exponential stability for larger z. And if we look at the closed loop system, then we have now a new blue term, which shows up in the linear part, which is exactly giving us exponential stability of the F, which was a necessary condition, you remember, due to the saturation. And we have the saturation here. So the question now, if we want to apply the previous theorem, was to know if there exists a common Lyapunov function for those two operators. Actually, the former Lyapunov function that we have introduced at the beginning is indeed a common Lyapunov function for those two operators. So if this one was coercive, then we get the result. Actually, this one was coercive if the P associated to A was coercive. So this is just this assumption that we need to add. So now we have the theorem that we have obtained with Daniele, Swan-Marx, and Christophe. Assume that the operator A generates a C0 semigroup, which is exponentially stable, and there exists a P, a bounded coercive, Important, linear self-adjoint positive operator satisfying the Lyapunov inequality. Moreover, the Shu-Gerby assumptions that we had before. Then we get the existence of small coefficient ki such that the equilibrium of this system is globally exponentially stable. Here we have the anti-wind-up modification of the integral action. Okay, so we have exponential stability of this semigroup. But do we get regulation? In fact, since we have modified the integral action here, we don't necessarily get regulation. So this is what is written here. The equilibrium exists, but we don't always have regulation. So if z is small, then we recover the nominal integral action. So in fact, what we need to be sure is that the perturbations that we have introduced are sufficiently small so that the equilibrium at the equilibrium z is small, so that the saturation of the anti-wind-up technique is not active. So we can formalize it mathematically. It says that if D and Y ref are satisfying this property, then the regulation is obtained. Now I'm going to enter into the last part of my presentation. And as we saw, if we want to impose exponential stability, it gives you a strong requirement. You need to modify the integral action. So now we will try to see if we can remove this constraint and still get asymptotic stability. So relaxing open loop exponential stability is the goal now. So again, our system, z dot equal y. Now we don't want to modify this part. We have our linear term with a 0, which means that this one is not exponentially stable. And we have our saturation. So can we have hope to obtain global asymptotic stabilization of this system? So if we don't assume open loop exponential stability, actually, this A can be, for example, conservative. This means that the control, not only we need to act on Z as before, you remember the control that we were using was KZ, but it will also need to act also on X. It will need to dissipate some energy also in the X space. But what we will, so in infinite dimension, we know that the stability of the open loop system is necessary for our problem. So we will assume weaker assumption of stability on A, just stability at the end. So here are the assumptions we make. So the operator A generates a C0 semigroup, which is just stable in the sense that there exists an operator P, coercive, such that this Lyapunov inequality is satisfied. We also assume that the pair A B star P is approximately observable. In other words, it means that for every x0, if the so ext is my semigroup associated to A, so if this is equal to 0, then the only solution is x equal to 0. It's approximate observability. And the last assumption, since we will use LaSalle, is that the domain of A is compactly injected in X. X is my Hilbert space. So if we go back to the paper of Slemrod in 1989, with exactly this assumption, he has obtained that if you pick U equal B minus B star P of X, then he has shown that the origin of this system is globally asymptotically stable. So what we want to do is to extend Slemrod result to the case in which we had an integral action. And if we look at the proof of Slemrod, this one is based on the use of a weak Lyapunov function. The fact that this operator is M dissipative, you remember that the saturation, as I mentioned, is increasing. So in fact, you can show that this operator is M dissipative. And at the end, we use LaSalle. LaSalle can be employed due to the fact that we have pre-compactness of trajectories due to the fact that the domain of A is compactly injected in X. So we want to add the integral action. We need two further assumptions. The first one is the fact that A, even though it's just stable, we will ask it to be invertible. And also that A minus 1 is bounded. So 0 belongs to the resolvent. The last assumption is one assumption that you have already seen many times. CA minus 1B is full rank. Since we have only one control, we can simply say that this is equal to 1. Actually, invertibility of A and the rank condition are necessary conditions for the regulation in finite dimension. So they are not minimal because we are asking A minus 1 to be bounded, but not so far. And the result that we have obtained is that if we pick M, still the same M as before, CA minus 1, then there exists a K, an operator, which is given here. So this part of this operator is acting on X, this part is acting on Z, and this gives us our feedback. So you see there is now a term in X. With this feedback, the origin is globally asymptotically stable. And very quickly, a sketch of the proof. So with this Lyapunov function, related to this Lyapunov function, the exact same Lyapunov function as before, this introduces a new state space in which the operator, the nonlinear operator, is M dissipative. And moreover, you can see that W dot is equal to this, is upper bounded by this term. So we have the exact same K as this one here. So KXE times SAT of KXE. So what we need to do is to follow what Slemrod has done, show approximate observability. This requires a little bit of work, but we can show that if this output is approximately observable, plus the fact that A is invertible, then this output is approximately observable for the complete system. Based on that, we just have to follow what Slemrod did in his 89 paper, and we obtain, indeed, asymptotic stabilization. So this gives us a procedure for a dissipative linear system with saturated input and with approximately observable output. So what we need to do, if we want to introduce an integral action, is first to construct an operator M, which has to be equal to CA minus 1. So basically, this M, this operator, it can be written as an operator on the solution, such that M dot is equal to Z dot, so Y, in fact, plus M0 times the saturation. You don't see it from what we had before, but this is exactly asking that M is equal to CA minus 1. And this M0 is exactly CA minus 1B. I want to write it like that because I want to not necessarily to apply it to bounded B. And then we construct the Lyapunov function W as V again, plus what we had before. And the main step of the proof will be first to show M dissipativity of the closed loop system, and then observability with this new output. We can apply this procedure, for example, to a wave equation. So we have a wave equation with this boundary condition and a saturated control in yx1 of t. And those are the initial condition and again a boundary condition. So if we just look at this system, the stabilization of this system with the saturated input has been addressed in a paper by Christophe Prieur, Sophie Tarboyesh, and João da Silva in 2016. Here, with what I have showed you, is now we can add an integral action. Indeed, we have the integral action. Then we need to find the m, which satisfies this equation. Actually, this m, this function of time, satisfies this equation. Then we can construct our Lyapunov function. And then what needs to be done is just to show so technicalities. So you need to show m dissipativity and observability, but the main approach is the same. And you can show that you get a Lyapunov function which satisfies this property, from which you get the control, which is given here, which gives you asymptotic stability of the PDE system with saturation and the integral action. So, some remarks. We have just shown asymptotic stability of the origin, but actually we don't know at all if we obtain regulation. So this is an open question. What type of result, which type of perturbation can be removed? I don't know yet. Also, the same technique can be employed when we consider internal model. Now, not only integral action, but internal model. And this has been, this is a paper that we have submitted to MICNA. And the general case with general internal model is under investigation. And now I arrive to my conclusion. So I gave you a technique based on forwarding. It was inspired by forwarding to construct Lyapunov function for output regulation in PDEs. It is based on this M, which is equal to CA minus 1, and this construction. So in the nominal case, the control can be simply taken as a parameter times Z, or when we have with the, I forgot to add the capital KI matrix. But the parameter KI that we obtain, so we have a value, but this value may be small. Actually, in 2018, Jean-Michel Coron and Amaury Hayat, they have introduced some modification on the Lyapunov function, which allows us to obtain a better term, KI, on some specific PDE. It was a transport equation, a nonlinear transport equation. So since we have a Lyapunov function, indeed, we can extend this result to nonlinear PDE. And this is exactly what we have done with saturation. So when we have a saturation, to obtain exponential stabilization, you need to modify the integral action by anti-wind-up technique, as we have shown. If you don't want to modify the anti-wind-up technique and forget about exponential stabilization, then with LAAS, you can obtain dissipative results for dissipative systems. So, and what we are doing at the moment is doing more general internal model with LINGMA, and there is one that has been submitted to MICNA. The last slide is this one, in which I give the 3 papers on which has been based this presentation. All the theorem has been proved. You can see the proof in those papers. So there is the first paper with Alexandre Teranjan, Valérie, and Chen-Dong Xu, and the second one in CDC 2022. And the last one is the paper that we just submitted to IEEE TAC. Thank you.